Question 5. The question says, this question deals with two uses for emitter followers. Part A is this arrangement. It says, an emitter follower is used to interface a loudspeaker to the rest of an audio system. The circuit diagram is shown below. So, having a look here, you can see you've got a transistor, and you see you've got a loudspeaker here. They give you the impedance of the loudspeaker, and they show that you've got an input going to the base of the transistor. It says the input voltage is 2.3 volts. It then says calculate the voltage across the loudspeaker. Now this is nice and easy. All you have to remember is that if you've got 2.3 volts here, there's going to be a 0.7 volt drop across here, and the rest is going to be here. So it's just 2.3 minus 0.7, which is 1.6 volts. Easy. Easy mark. Second question says, estimate the input impedance of this arrangement. Now, what you need to know is that the input impedance here is going to be a part of this impedance of this loudspeaker, because that's the only thing giving any resistance. But that impedance is going to be amplified, if you like, thinking about it that way, it's going to be amplified by this gain here. So, if you just remember that it's just going to be HFE times by RL is going to be input impedance, then you can't go wrong, because they're not going to ask anything different to that. So, you've got 8 ohms here, and you've got 50 here, so the input impedance is going to be 50 times by 8. And that's an approximation for the input impedance, because that's never going to be perfect. So 50 times 8 is 400 ohms, and the answer is approximately 400 ohms. Excellent. Now, the last part says, an AC signal ranging from minus 2.3 to plus 2.3 is now applied to the input. What modification must be made to the circuit to prevent distortion? Now, this modification, all you can remember is that for an AC signal, preventing distortion is done by using a push-pull amplifier. That's this circuit where you have two transistors connected up together, going into a load which then has a 0 volts. So that's what you need to remember, that will prevent distortion of an AC signal, because the two transistors, one will conduct at negative voltages and one will conduct at positive voltages. So the answer here is just to use a push-pull amplifier. Now if you can, go into more detail than that, but don't go too far because it is only one mark. Part B gives you another circuit diagram, and it says the circuit diagram here shows a voltage regulator which incorporates an emitter follower. So that's this whole arrangement here. And you can see you've got your emitter follower transistor going on here with voltage divider here. The first part says the supply voltage, Vs, is 12 volts. Calculate the voltage V1, so that's the voltage dropped across the resistor. Now, you can always remember that as long as this Zener diode is in breakdown, the voltage across it is going to stay constant, no matter what this is. So this can be 13, 14, 15 volts, this will be the same. So, and that's written nicely there for you. So V1 is just going to be the voltage dropped here minus the voltage dropped here. So the entire voltage dropped minus this. So we know the supply voltage is 12, and we know the voltage across the Zener is 7.5. So we know that the voltage V1 here must be 12 minus 7.5, which is 4.5 volts. Nice and easy. You just remember that that has got to add up with that to make that. Now, it then says the output voltage Vout can be changed by adjusting the 10 kilo ohm variable resistor calculate the maximum and minimum possible values of V out, that's here, using this arrangement. Now, we see this is a Zener diode, and in the front of the paper, you're given a few formulae to help you out. And one of them is that for a stabilised power supply, V out, right here, V out is VZ, that's this, VZ across the Zener, times by 1 plus RF over Rin. Now, you can use this formula to help you out here and do this question. So, making sure that you see which is the maximum value and which is the minimum value, because you think that they would have minimum here, maximum here, but they don't. So, making sure you've worked that out. First one is easy. The minimum is going to be when this is 0. So, RF over Rin equals 0 over 30, which is always going to be 0. So that's nice and simple, because then V out is VZ times by 1. So V out at its minimum value is just going to be VZ, which is 7.5 volts. And then, same again for the second part, except this time it's at its maximum value. Now the voltage is going to be at its maximum value when this resistor is at its maximum value, which is 10 kilo ohms. So we now have V out equals VZ 1 times 1 plus 10 over 30. And both of those will be in kilo ohms, but they cancel, so that's fine. So we now have V out equals 7.5 times by 1 plus 1 over 3. So I do this with fractions. You can do it however you want. It's a calculator paper, so just do it with your calculator. So that's 7.5 times by 4 over 3, which I know from previously to be 10 volts. So that's now goes into the maximum value. And once you've worked out the two, make sure, saying it again, because I did get caught out on this before, you've got maximum here, minimum here, making sure that you're writing them the right way around. And then that's a good couple of marks you can get just by using that formula in the front of the booklet. Now, the last part of this question says the supply voltage, Vs, increases to 13 volts. So we're now looking at 13 volts up here. Explain why the output voltage, VL, remains unchanged. Now, we know from this that VL is VZ 1 plus RF over Rin. So, VZ is always going to be 7.5 volts, unless there are special circumstances. But in this circumstance, it's always going to be 7.5 volts, no matter how much that changes to. So, we know from this equation that Vs is completely independent. So there are various ways you can explain it, and the way I say it is the output voltage is determined by the Zener voltage, as the equation states, Vz times by 1 plus RF over Rin. The Zener diode is in breakdown, and so the voltage will stay constant. The mark scheme, just get the mark scheme so we can see other ways of saying that. The mark scheme says the voltage across the resistor changes to leave 7.5 across the Zener, so the output will remain unchanged. Now that's the same thing being said there, but what they're saying is that a change of this supply will change this voltage V1, and this will stay the same. And then the output voltage is dictated from 7.5 volts, and so the output is always going to stay the same. The only way to change the output is by changing this resistor value, or by replacing and changing this resistor. But for this question, all you're remembering is the main thing to remember is that VZ is the thing that affects V out.